Hi everyone, welcome back to the channel. Let's start. May-June 2025, variance 42, paper 4, structured question. Let's see what we have in the first question. Seems like the first question related to group 2. Um, calcium nitrate decomposes on heating. Write an equation for the decomposition of calcium nitrate. So answer is going to be very easy. This is your calcium nitrate. On heating, it undergoes thermal decomposition, and as a result, it will turn to calcium oxide, nitrogen dioxide, and oxygen. So if you use 1 mole here, obviously it's going to be 2 and it's going to be half, all right? But whenever we use 2 moles of calcium nitrate, obviously it's going to be 2 moles of calcium oxide, 4 moles of NO2, and 1 mole of oxygen gas. So both the equations are acceptable in the examiner's, from the examiner's perspective. Both equations are acceptable, whether you need to write 1 mole or whether you need to write 2 moles. All right, so both are acceptable. By the way, nitrogen dioxide has a dark brown color. You should remember this. Next part of the question, describe the trend in the decomposition temperature of the group 2 nitrate. Explain your answer. Since we have 3 marks, which means we need to give each and every detail, all right? So down the group, ionic radius increases. So when ionic radius increases, charge density decreases. And when charge density decreases, polarizing power of cation becomes weaker. That means cation cannot distort the electrons of nitrate ion easily. And therefore decomposition temperature increases down the group. In other words, we can say down the group, thermal stability of group 2 nitrates increases. All right. Let's move on to the next part of the question. A sample of 0.33 gram of strontium oxide, SRO, so mass of sample of strontium oxide is given, is completely dissolved in distilled water to form a solution of strontium hydroxide. All right, so let me give you an equation here. Strontium oxide, when placed in water, it will turn into strontium hydroxide. And strontium hydroxide is basically an alkaline solution. The resulting solution, that means strontium hydroxide, is added to volumetric flask and made up to 250 cm3 with distilled water. Calculate the pH of the solution at 298 Kelvin. Give your answer to 2 decimal places. All right. So examiner is looking for the answer up to 2 decimal places. So what we can do here is, first of all, we need to find out the MR of strontium hydroxide. Oh, I'm sorry, strontium oxide. So strontium has a relative atomic mass of 87.6, and oxygen has a mass of 16. When you add these two values, you will get 103.6. All right. Since we know the mass and we know the MR, we can find the moles. So in the second step, let's find the moles of strontium oxide. So it's 0.333 gram divided by 100 and 3.6. So it's going to be 3.21 in. All right. I'm going to use this equation, obviously. So let me write it down here. Strontium oxide is dissolving in water, converting into strontium hydroxide. Now, according to the equation, strontium oxide and strontium hydroxide both have 1:1 ratio. So when we got 3.21 into 10 to the power minus 3 moles, obviously I'm going to get the same number of moles of strontium hydroxide. So it's going to be 3.21 into 10 to the power minus 3 moles. All right. Now I've got this moles in 250 cm cube volume. All right. So 250 cm cube contain 3.21 into 10 to the power minus 3 moles. In order to get the pH value of this solution, I need to convert these moles into concentration, and for that I need to compare it with 1000 cm cube. So concentration of strontium hydroxide is going to be 0.01285 mole per dm cube. All right. So let me ionize this strontium hydroxide. Let me ionize this strontium hydroxide in the next step. It will turn to strontium ion and two hydroxide ions. Now this strontium hydroxide and hydroxide ion has 1:2 ratio. When we have 0.01285 mole per dm cube, which is also called molar, obviously I've got concentration of hydroxide ions. I think it's 0.0257 mole per dm cube. Now in the next place, once if we know the concentration of hydroxide ions, we can find the value of pOH by using this expression. So concentration is 0.0257. So pOH is going to be 1.61. Now, in order to find the pH of this solution, I'm going to use an expression of pH plus pOH equals to 14. So when I'll subtract 1.61 from 14, I'll get 12.38, and obviously it's going to be 12.34, and that's my answer. All right, I hope it makes sense to you. So that's an easy question, and I believe you have got the logic behind this whole part. And this question has 4 marks, which is why I need to show all the steps so that you will get the idea what's going on behind this whole question. All right. So that's the end of first question, and I'll start the second question. All right. Let's start with the question number 2. Seems like this question belongs to transition element, and transition element is one of the most important chapter in entire A2 chemistry, because this chapter will give you 28 to 30 marks out of 100. All right. So that chapter is very, very important, very, very crucial in order to get an A star in this subject. All right. Let's start with this question. When cobalt 2 sulfate is dissolved in distilled water, solution A is formed. Let me give you a hint here. So when cobalt 2 sulfate is dissolved in water, it will give you a complex compound like this. Okay. And this complex compound has a pink color. The reaction scheme in figure 2.1 shows some reactions of solution A. When solution A is treated with NaOH, obviously solid B is formed. So what's going on actually here? Let me show you. When pink solution of cobalt 2 ions or cobalt 2 sulfate is treated with NaOH, I'll get sodium sulfate, and due to acid-base reaction or precipitation reaction, I'll get precipitate of this complex, okay, along with water molecule. And this precipitates has blue color. All right. So solid B is basically this compound, which could be written as, according to my lecture, it could be written as like cobalt hydroxide dot 4H2. So blue precipitates, the formula of blue precipitate is this. All right. Now, when this compound is treated with aqueous ammonia, solution C is formed. So let me give you an equation here. So what's is actually happening when solid B and aqueous ammonia is treated together? This is blue precipitates. All right. And when you add excess amount of ammonia, ligand substitution reaction takes place. And because of that, you will get a complex sign okay. So this is basically blue precipitates, and you will get a yellow-brown solution in this scenario. All right. So that's called ligand substitution reaction. We know in a spectrochemical series, we have done that in the class. Ammonia is a stronger ligand than both hydroxide and water, which is why ligand substitution reaction takes place. This ammonia substitutes hydroxide ions and then later on water molecule, which is why ligand substitution reaction takes place. And as a result, you will get cobalt 2 ions, and that cobalt 2 ions with ammonia ligand shows yellow brown color. Okay. Part 1. Complete table 2.1 to show the formula and color of each of the cobalt 2 containing species present in A, B, and C. Identify the type of reaction forming each of B and C. So formula of cobalt containing species. So that is your A, that is your B, and that is your C. All right. So I'm going to write cobalt, water, and sulfate ions. Color is going to be pink. And type of reaction is basically, it's just, we are dissolving the compound actually. So it's standard enthalpy change of solution, you could say. All right. Now in B, you can write CO, H2O, taken 4, OH taken 2, and then bracket, and that will give you blue precipitates. And this is acid-base reaction. Or we can write precipitation reaction, okay? Both are acceptable. This is precipitation short form, okay? Precipitation reaction and acid-base reaction. Both of them are acceptable, so you can write any one of them. Why it is an acid-base reaction? Because this complex ion will serve as an acid and NOH will serve as an alkali, which is why an acid-base reaction takes place, okay? Now in part C, I'm going to write CONH3 taken 6 2 plus, and its color is going to be yellow brown. And the type of reaction is ligand exchange or ligand substitution reaction. Both are same. So you can write any one of them. So ligand substitution reaction. In the next part, suggest a suitable reagent for the formation of this complex ion from solution A. So what's happening is, when this compound is treated with compound something here, I mean compound X, you will get this compound. Technically, chloride ions are substituting water molecule, and the source of chloride ion could be either concentrated NaCl, could be either concentrated ammonium chloride or concentrated hydrochloric acid, which means I'm going to react solution A with either concentrated hydrochloric acid or concentrated sodium chloride or concentrated ammonium chloride. So suitable reagent could be like this, but let me show you the equation. This is aqueous solution of cobalt 2 ions. They are reacting with excess chloride ions, and due to ligand substitution reaction, they will form this complex ion. Okay, so this chloride ion needs to be concentrated, which is why ligand substitution reaction takes place. If it's going to be diluted, reaction cannot take place. Okay, if chloride ions is diluted or in a diluted form, reaction won't occur, reaction won't take place. In order to do the reaction, we need concentrated solution. Okay, so I'm going to write concentrated hydrochloric acid or concentrated sodium chloride, because we need a source of chloride ion. So both of them are correct. You can write any one of them. Next part, the complex ion has tetrahedral geometry. That's true. The 3D orbital in an isolated cobalt 2 ions are degenerate. Degenerate means equal energy orbital. Means all 5 orbitals have identical energy. All right. Complete figure 2.2 to show the relative energies of the 3D orbitals in an isolated cobalt 2 ions and in cobalt 2 ions in a tetrahedral geometry. So in an isolated scenario, this is dxy, dxz, dyz, dx squared dash y square and dz square. dxy, dxz, dyz, dx squared dash y square and then dz square. And all of them have identical energy, right? Um, um, First of all, let me get the electronic configuration of cobalt 2 ions. Now, cobalt has an atomic number of 27. So I'm going to use short form of electronic configuration. So in place of 18 electrons, I'm going to write argon. Then we have 3D, and then we have 4s. Now 4s electrons, 4s2, 2 electrons are moved from the 4s. So 3D contain, I believe, 7. So I'm going to distribute these 7 electrons in this isolated d orbital. 1, 2, 3, 4, 5, 6, and this one is 7. Now in tetrahedral complex, the first 3 experiences more repulsion, because in tetrahedral geometry, all the ligands exist between the axes. I repeat, in tetrahedral complex, all the ligands exist between the axes. These 3 orbitals also exist between the axes, which is why repulsion becomes stronger, and therefore they will exist as higher energy orbital. Whereas these 2 exist on the axis while ligand exists between the axis, which is why they will experience lesser repulsion and therefore they will exist as a low energy state. So what we can write here is that the first 3 d orbitals has higher energy and the last 2 d orbital has lower energy. Let me distribute the electrons. I need to distribute 7 electrons in these d orbitals, right? Okay, so we don't need to distribute the electrons technically. So we just need to distribute the d orbitals like this. Okay. Uh, I repeat. I need to repeat one more time. In tetrahedral complex, all the ligands exist between the axes, whereas these 3 orbitals also exist between the axes, which is why they will experience more repulsion, and they will settle as higher energy orbital. According to my lecture, these set of higher energy orbital is going to be T2G. All right. These 2 orbital exist on the axis, whereas ligands in tetrahedral complex exist between the axes, which is why they will experience less repulsion, and therefore they will exist as lower energy orbital, and this is going to be represented by Eg. By the way, I have given you a very detailed, information in my lecture, so you can check in the playlist where you will get the transition chemistry whole chapter, and then you can learn it from there also. What's actually happening behind the repulsion? All right, what's the reason behind the repulsion? Anyway, let's move on to the next page. Draw a 3-dimensional diagram to show the structure of the complex ion is this. 3-dimensional structure means 3D structure, and obviously this complex has ML4 situation. So whenever we have 4 similar ligand attached to transition metal ion, the geometry is going to be tetrahedral according to my lecture, if you remember. So this complex ion has a tetrahedral geometry, and I'm going to make it like this. This is cobalt. Since it is 3D, so we need to draw dotted line and pyramid. And these arrow represents dative bond. So technically these chloridines forms a dative bond with the transition metal cobaltine. Let me put the bracket here and a charge on it. That is 2 minus. And that's the protocol you need to follow in the paper also, okay? Now, part C seems to be related to electrochemistry. H2O2 is acting as an oxidizing agent or a reducing agent when reacting with the species that contain manganese. All right. Table 2.2 shows electrode potential for some electrode reactions. Use only a species listed in table 2.2 to suggest one reaction in which H2O2 acting as an oxidizing agent. The, the, the more positive the SCP value, the stronger the oxidizing agent. So among these, the more positive the SCP value is going to be this one, which means this H2O2 is acting as a strong oxidizing agent, okay? And that's what we have done in the class. Let me write it down. More positive SEP value stronger oxidizing agent. All right. That means I'm going to use this equation and this equation. All right. So let me write it down, both the equations first. This is H2O2 plus 2 hydrogen ion plus 2 electron, reversible sign 2H2O. Okay. According to my lecture, uh, half cell with a less positive or negative SCP value will need to be flipped in order to write the equation in oxidation form. So in order to write this equation in oxidation form, I need to flip the equation. So when I'll flip the equation is going to be like this: Mn OH taken 2 plus 2 OH negative, reversible sign MnO2 plus 2H2O plus 2 electron. Since the number of electrons are balanced, I need to cancel them. So cancel the number of electrons, and whatever left on the left hand side as well as on the right hand side, you can write it. And that's going to be your full cell equation. So let me write it here. This is H2O2 plus 2 hydrogen ion plus 2 hydroxide ion plus manganese 2 hydroxide is going to be converted into MnO2 plus this 2H2O, and this 2H2O is going to be 4H2O. And that's your full cell equation, all right? I hope it makes sense to you. By the way, examiner is looking for the standard cell potential value, all right? Examiner is looking for the standard cell potential value. My goodness, hold on. Okay. And an overall equation. So I've written the overall equation. I've got the overall equation, but I need to find out the E naught cell. And for E naught cell, I'm going to use a formula. E naught cell equals to E naught right minus E naught left. So I'm going to plug in the value in this formula. It's basically 1.78 minus 0. 0.04 so it's going to be how much? Plus 1.82 volt. Okay. Now here we have one question. All right. Some student thinks that we can use these two values also. All right. So this could be written in reduction form, and this could be written in the oxidation form. And for that, we need to flip the equation. That can also happen in the that can also an alternative answer, right? But look at this. The cell potential between these two half cell is going to be relatively lesser as compared to these two half cells. So when we determine the E naught cell value between these two half cells, you'll get more value, more E naught cell value. And when we use these two equations in order to get the E naught cell, I'll get lesser value. So we need to consider that those equations which will give you more E naught cell rather than the lower E naught cell, which is why I'll use first and third equation to get the answer. Now in this, H2O2 is an oxidizing agent because it oxidizes Mn2 plus and converted into Mn4 plus. That's the whole scenario. H2O2 is acting as a reducing agent. The lower the less positive value, this acting as a reducing agent. So I'm going to use this value and this value. All right. Again, if I'm going to use this equation and this equation, I'll get the lesser amount of E naught cell. So in order to get the higher amount of E naught cell, I'm going to use these two equations to get the answer. So this equation needs to be written in reduction form. So I'm going to write this equation as it is. MnO2 plus 4 hydrogen ion plus 2 electron Mn2 plus 2 H2O. All right. Now I need to flip this equation in order to write it in the oxidation form. So I'm going to reverse it. If I'm going to reverse it, it's going to be like this. O2 plus 2 hydrogen ion plus 2 electron. As the number of electrons are already balanced, we need to cancel them out. So the overall equation for this reaction is going to be like this. Let me find the value of E naught cell for this overall equation. So I'm going to plug in the value in the formula, which is going to be E naught right minus E naught left. E naught right must have more positive SCP value, which is going to be plus 1.22 volt. And E naught left is going to be less positive SCP value, which is 0.68 volt. So the answer for this part is going to be plus 0.54 volt. Okay, let me show you one thing. Here in this compound, manganese has an oxidation state of +4. All right. So in this equation, H2O2 is acting as a reducing agent, which is why it changes oxidation state from +4 to +2. All right. I hope it makes sense to you. I hope you get the logic, you get the point. Let's move on to the next part of the question. That seems like a very, very huge question. Very, very lengthy question. Acidified magnate 7 ions can be used to analyze the content of iron tablet by titration. And that's what you have done in O levels ATP. That's what you have done in AS practicals. That's what you have done with me in AS theory also. By the way, acidified magnate 7 ions has a purple color. And also it is acting as an oxidizing agent. 2 identical iron tablets are crushed and dissolved in distilled water. That's very, very important. 2 iron tablets. The resulting solution is made up to 150 cm cube with distilled water. That's very important again. So I'm going to use a volumetric flask for that dilution. Okay. Now 25 cm cube of this solution require 18.6 cm cube of this concentration of magnate ions to reach the endpoint. All the Fe2 plus ions are oxidized. The relevant half equations are shown, and we need to balance this equation. In order to balance this equation, I need to multiply this equation by 5 so that I'll get so that number of electrons can be balanced. As the number of electrons are balanced, they will cancel out. And the final equation for this reaction is going to be like this. MnO4 negative plus 8H positive plus 5 Fe2 plus arrow 5 Fe3 plus Mn2 plus 4H2O. Okay. So that's the overall equation. And we have done that equation in lecture A2 and AS also. Describe the color change observed at the end point. Well, in titration, you know that iron 2 sulfate has to be in the conical flask, and iron 2 sulfate has a green color. All right. When you add certain amount of sulfuric acid in that particular conical flask, color changes from green to colorless. All right. When you add KMnO4 from the burette into the conical flask, obviously the color changes is going to be from colorless to pink. And that is the area in which a student lost usually marks, because they have written purple to colorless, which is incorrect. It has to be colorless to pink, because color observation always comes from the conical flask, not from the burette. You have to keep this in mind. Okay. Now calculate the mass in milligram of iron in 1 tablet. Okay, 1 tablet. We have given 2, but we need to find the mass in milligram for 1 tablet. Assume all the iron in the tablet is Fe2 plus. Show your working. Okay, I'm going to show this working. So we know the concentration and volume of KMnO4. That means I can find the moles. So first step of this calculation is get the moles of magnate 7 ions. So it's basically 0.05 into 18.6 divided by 1000. So I'm going to get 9.3 into 10 to the power minus 4 moles. Okay. Now we know the molar ratio between magnate ions and iron 2 ions is 1:5. So using this molar ratio, I'm going to get the moles of Fe2 plus ions. So magnate ions and iron 2 ions has 1:5 ratio. When we have 9.3 into 10 to the power minus 4 moles, so moles of Fe2 positive ions is going to be 4.65 into 10 to the power minus 3 moles. Okay. Now, I've got this much moles in 25 cm cube, and you know that uh, I have diluted the solution till 150 cm cube, so I need to compare these two volumes. And the third step, 25.0 cm cube contain how much moles? 4.65 into 10 to the power minus 3 moles. Of Fe2 plus ions. We have used 150 cm cube for dilution. So moles of iron 2 ions in this dilution is going to be 0.0279 moles. In the next step, I'm going to get the mass of iron. So I'm going to use moles. 279 into mass of iron. Mass of iron is basically 55.8. So I'll get 1.55612 gram. I'm going to change, and this 1.55612 gram for 2 tablets, all right? So let me get the mass of iron per tablet. So it's basically 1.55612 divided by 2. You will get 0.77841 gram. So to convert this into milligram, we need to multiply by 1000, and it's going to be, hold on. Hold on. Yeah. So I need to multiply this by 1000. Mass in milligram. So it's basically 0.77841 into 1000. So it's going to be 778.41 milligram. Okay. I hope it makes sense to you. That's the end of second question. I'll start with the third one. Let's start with the question number 3. Define entropy. In entropy, there is a dispersal of energy from system to surrounding, and surrounding to system takes place, which is why we need to add this statement along with the usual definition, all right? So disorderness of the system in which dispersal of energy takes place from system to surrounding and vice versa. Next part of the question is, figure shows how the entropy of a pure substance changes with temperature. So technically, when temperature increases, entropy की value also increases. Okay, identify the process occurring at each of the temperature T1 and T2. So technically, it is a change of state from solid to liquid and liquid to gas. Okay. So this is technically your solid part. And this becomes solid plus liquid. And this become gas. So gas has the highest entropy value as compared to liquid and solid. So this process is going to be melting. And this process is going to be boiling. All right. So first, solid changes into liquid, then liquid and solid both exist simultaneously, then liquid will turn to gas. The first stage is melting and the second stage is boiling. So I'm going to write melting and boiling. Okay. Now, in the next part, explain why the entropy change at T2 is bigger than the entropy change at T1. I've told you that gaseous molecules have higher entropy value because they have extreme random motion. So they will have extreme disorderness in the system, all right? So what we can write here is at high temperature, liquid will turn to gas. And gas has highly irregular arrangement of particles exhibit this more disorderness. Hence, it has higher entropy value at higher temperature. All right. Now in the next part, the equation for the reduction of iron 3 oxide by carbon monoxide at 450 degrees Celsius is shown. That's called reduction reaction, and the delta G naught is negative. That means reaction is spontaneous and reaction is likely to proceed in the forward direction. In other words, we can say reaction will take place. All right. So figure 3.1 shows the enthalpy of formation and the entropy for some substances. Using the data in the table 3.1 to calculate the entropy of carbon monoxide at 450 degrees Celsius, show your working. Okay. Okay. In the first step, I'm going to get enthalpy change of reaction by using the formation data. Okay. So let me write the equation again. My goodness, that's a huge calculation area. It has a lot of calculation, a lot of steps. Fe2O3 is reacting with carbon monoxide. By the way, this reaction you have done in O levels in extraction of iron through hematite ore. Okay. I thought I should let you know about this equation. And you will get carbon dioxide. I need to find out the enthalpy change of reaction. And since formation data is given, so I need to make Hasse-Law cycle. And obviously arrow needs to be upward. Now Fe2O3 has a value of minus 824.3. Carbon monoxide has a value of minus 110.5. I need to multiply this value by 3 because this equation has 3 moles. Now carbon dioxide has a value of minus 393.5. And I need to multiply this value by 3 again because carbon dioxide has 3 moles in the equation. Now there is no value of iron here because for diatomic molecules and for elements, standard enthalpy change of formation is always 0. All right. So I'm not going to use value of iron. Make an arrow in the clockwise direction and rearrange the values, and then I'll get the answer. Now this value and these 3 values have to be positive. This value has to be taken negative, and I'll equate all the values equals to 0. So this is delta HR. This value is positive plus minus 824.3 plus minus 110.5 times 3. So I have to take these values as positive. Now I'll take carbon dioxide value is negative, minus 393.5 into 3, and this becomes equals to 0. So the delta H, the enthalpy change of reaction for this equation is going to be minus 24.8. kilojoules per mole. Okay. Now in the second step, I'm going to use this relationship, delta HR minus D delta S system. So delta G naught is already given in kilojoules, which is minus 36.2. Delta HR is already given minus 224.8 minus temperature. Temperature is what? Temperature is 450 degrees Celsius. Now I need to convert this value into Kelvin. So it's going to be how much? It's going to be 723 Kelvin. I'm going to use this value here. And then I'm going to use, or I'm going to find entropy change of system. So from here, the standard entropy change of system is going to be how much? Minus 15.8. And obviously it has to be joules. Okay. In the third step, I'm going to use an expression in which I'm going to use summation of standard entropy of product minus summation of standard entropy of reactant. Now product has carbon dioxide and iron. Now carbon dioxide has a value of 213.8. And obviously I'm going to multiply this value by 3 because in equation we have 3 moles. Plus iron has a value of 27.3. I'm going to multiply this value by 2 because in equation we have 2 moles of iron. Minus product. Product is Fe2O3, which is 87.4. Plus I need to find out the value of carbon monoxide, and we know that in equation we have 3 moles of carbon monoxide, which is why I'm going to write 3x here. And now system, we have calculated the value of standard entropy change of system, which was minus 15.8. So I can find the value of X from here, and the value of X, I believe, is going to be 197.6 joules. Okay. So that's the answer for this part. Next is iron 2 oxide can also be reduced to iron by carbon monoxide as shown. Okay. This equation is applicable for 1 mole. Oh, that's different equation. Okay. So delta H is already given. I mean, enthalpy change of reaction is given. Standard entropy change is given. So examiner is looking for an explanation in which if we increase the temperature on the feasibility of this reaction, what happens if we increase the temperature? So look at the data. Both enthalpy and entropy are positive. Let me show you what we have done in the class. This is delta G naught equals to delta H minus T delta S naught. Now, according to the question, if enthalpy change is negative, minus T will remain as it is, and standard entropy is also negative. Look, this value is negative, this value is negative. Okay. So this negative value will remain as it is, and this minus minus becomes plus. All right. So when we increase the temperature, obviously this entire T delta S naught term becomes more positive, and so delta G becomes more positive, and delta G becomes more positive. Obviously, reaction is not going to be feasible or spontaneous. So delta G naught is going to be positive at high temperature. So what we need to write here is at high temperature, T delta S naught term becomes more positive. So delta G naught is also positive. Hence, reaction is not feasible. Or spontaneous at high temperature. I hope it makes sense to you. I'll start with the third question. All right. So the next question is question number 4. In aqueous solution, iodide ions react with acidified hydrogen peroxide as shown in reaction 1. By the way, in this reaction, iodide ion is acting as a reducing agent, whereas hydrogen peroxide is acting as an oxidizing agent. The rate equation for reaction 1 is shown. All right, from this rate equation, we conclude that both hydrogen peroxide and iodide ion have first order reaction. All right, so in the first part of the question is, what is meant by order of reaction? Oh, that's easy. Power to which the concentration is raised in the rate equation is called order of reaction. In the next part, complete table 4.1. The order with respect to hydrogen ion is technically 0 because it is not given in the rate equation. If any substance is not given in this rate equation, which means that substance has 0 order, which means the concentration of that particular reactant has nothing to do with the rate equation or rate of reaction. Okay. Now, with respect to iodine, it is first order. With respect to H2O2 is first order, and we need to get the overall order, so we need to add these two values. So I'm going to get 2. That means the overall order is going to be second. Sketch a line on figure 4.1 to show the relationship between concentration of iodine and time. Since iodine has first order reaction, and in first order reaction, the concentration and time graph has to be like this, in which constant half-life is observed. Okay? And we have done this in class also. Next, nitrogen dioxide reacts with ozone as shown in reaction 2. Okay. The nitrogen dioxide is reacting with ozone, converting into N2O5. That compound is called dinitrogen pentoxide and oxygen. The rate equation for reaction 2 is shown, which means both NO2 and ozone have first order reaction. 2 experiments are carried out to measure the rate of reaction 2. In the first experiment, the initial rate is measured starting with known concentration of NO2 and ozone. In the second experiment, the concentration of NO2 and ozone are both increased by a factor of 4. Predict how the initial rate for both two would change. Since uh, it is basically second order with respect to overall thing, so overall order is second. So if you increase by a factor of 4, so it's going to be increased by a factor of 16, all right? Because whenever you increase the concentration, rate of reaction becomes quadruple for second order. So this is a second order reaction, all right? So when you increased 4 times, it's going to be 16 times. Increased by a factor of 16. I hope you remember, we have done that in class. Whenever it is a second order reaction, and if we increase the concentration or if we double the concentration, rate of reaction becomes quadruple. So when we increased the concentration by a factor of 4, obviously initial rate is going to be 16, quadruple time. The reaction mechanism for reaction 2 has 2 steps. Define rate determining step. Slow step reaction is rate determining step reaction. Okay, in part third, suggest equations for the 2 steps of the reaction mechanism for reaction 2. Okay, in reaction 2. So I need to get this equation and I have to devise the mechanism. So first of all, let me react NO2 and ozone. NO2 and ozone are reacting together, converting into NO5. Now, in the second step, this NO5 reacts with another mole of NO2 because we have 2 moles in the equation. So it's going to be N2O5 and oxygen gas is given off. Now look at this. This is going to be your intermediate. So when you cancel out this intermediate, equation is going to be like this. 2NO2 plus O3 arrow N2O5 plus O2. And this equation is already given by the examiner in the question paper, right? That means the mechanism I have devised for that reaction 2 is absolutely correct. Also, examiner has given me an information about that. Both of them have first order reaction, which means both of them should take part in the slow step reaction. So step 1 is going to be the slow step because NO2 and ozone both are involved and both of them have first order reaction. So let's see what we have in the next page. Dinitrogen pentoxide N2O5 can decompose to NO2 and O2. The rate equation for this decomposition is shown. So rate, as concentration of N2O5 increases, rate of reaction also increases, which means both are directly proportional to each other. If both of them are directly proportional to each other, which means it's going to be the first order. And that rate equation also indicates the same explanation which I've given you. All right. Use figure 4.2 to calculate a value for the rate constant for this decomposition. So I need to find out the value of the rate constant for this decomposition. And since it is first order reaction, let me show you one thing. Rate equals to K concentration of N2O5. When we remove equality sign, I need to remove the constant sign. And when we remove both, I'll get the proportionality sign. So this indicates that concentration of N2O5 is directly proportional to rate, which is why you will get a graph of a straight line. Okay. So for first order reaction, rate equals to K concentration of N2O5. The rate of reaction is already given. From this value, I can find the rate of reaction. And this is going to be 15.0. Okay. So 15.0 into 10 to the power minus 4. And the concentration of N2O5 is going to be like this. That is 0.050. So I'll get the value of K from here. Rate is 15.0 into 10 to the power minus 4 equals to K. Concentration of N2O5 is 0.0500. So the value of K from here is going to be 0.030. Now in the next part, use your answer to C1 to calculate the half-life in seconds for this decomposition. Since it is a first order reaction, so for first order half-life, I'm going to use this expression 0.693 over K. I've got the value of K from in the previous part. So I'm going to plug in the value here as it is. So the value is going to be 23.1. Okay. So that's the end of this question. Let's see what we have in the next. Chloric 1 acid, HClO, is a weak Bronsted Lowry acid. When chloric 1 acid is added to aqueous sodium hydroxide, an acid-base reaction takes place as shown. Okay. So this is basically sodium chlorate 1 and water. This sodium chlorate 1 is basically your salt. Okay. Identify the two conjugate acid-base pairs in this reaction. Two conjugate acid-base pair. So if it is an acid, obviously this is going to be conjugate base pair. Okay. Conjugate base. The sodium chlorate 1 is basically the conjugate base. Why? Because it has negatively charged ion which accepts proton. So proton acceptor is basically conjugate base. Okay. Now in the second place, acid 2 is going to be water, and conjugate base is going to be sodium hydroxide. All right. I hope it makes sense to you. The value for the acid dissociation constant Ka of chloric 1 acid is given. Calculate the concentration in mole per dm cube of this at a pH of this. So, so pH equals to minus log under root Ka times concentration of acid. And acid is basically HClO, that is chloric 1 acid. We know the value of pH, which is 4.51, equals to minus log under root Ka. Ka is already given in the question paper, which is 3.70 into 10 to the power minus 8. And we need to find out the concentration of chloric 1 acid. So we have done such sort of question in the class. I hope you remember that. So obviously the concentration of chloric 1 acid from here is going to be, okay, let me solve this. In class, I've given you the steps. Let me show you the steps one more time. This is minus 4.51 equals to log under root 3.70 into 10 to the power minus 8 into concentration of chloric 1 acid. Now I'll switch log from here to there. Obviously, it's going to be then antilog. Antilog is basically the shift log, also called log inverse. Equals to under root 3.70 into 10 to the power minus 8 into concentration of HClO. Okay. Obviously, I've got the value from this. Press shift, then log, then minus 4.5, and then press equals to on the calculator. You will get the answer. Okay. So this answer is going to be like this: antilog minus 4.51 इसका स्क्वायर कर लेते हैं equals to 3.70 into 10 to the power minus 8 into concentration of HClO. And this antilog minus 4.51 square is going to be divided by the value, which is 3.70 into 10 to the power minus 8. So the concentration of HClO is going to be 0.02580 mole per dm cube. And that's the concentration. I hope you get the steps. If you have any issue in these steps, let me know. I'll give you the reply on the channel, okay? When a solution of HClO, that is chloric 1 acid, is heated, chloric 5 acid and a strong acid not containing oxygen are formed as the only product. Write an equation for this reaction. Now, chloric 1 acid has a formula of HClO. And chloric 5 acid is basically HClO3. That is chloric 5 acid. And obviously you will get an HCl also because this HCl has no oxygen atom. Now I need to balance the equation. And obviously how many oxygens we have here? 3. So put 3 here. How many chlorine atoms? 3. So put 2 here. How many hydrogen atoms? 2 plus 1, 3. And here 3 hydrogen atoms. So hydrogen is balanced, chlorine is balanced, oxygen is balanced, which means this equation is balanced. Define a buffer solution. Never write buffer solution doesn't change the pH. Never, ever write such sort of a statement in the paper. Instead, I have given you the definition. A solution which maintain its pH fairly constant upon the addition of a small amount of acid or alkali. Suggest a substance that could be added to aqueous ethanoic acid to form a buffer solution. In order to make a buffer solution, we need weak acid and salt of weak acid. That indicates in order to make a salt, I need to add sodium hydroxide in it. So ethanoic acid, when treated with sodium hydroxide, it will turn to sodium ethanoate and water. So in order to make a buffer solution, I need to add the salt. So sodium ethanoate is going to be added. To make a buffer solution. Okay. So sodium ethanoate is basically the core point, main point. But how did we get this? By adding NaOH in the solution, okay? Because there is no sodium hydroxide is given in the question. Okay, now let's move on to the next part of the question. Let's see what we have in it. Now, some fertilizers contain calcium dihydrogen phosphate. Okay, an aqueous solution containing dihydrogen phosphate ion can act as a buffer solution. Okay, write two equations to show how H2PO4 negative ions can act as a buffer. So this technically will have an amphoteric nature. So it can donate its proton, it can accept its proton also. Uh, okay. Uh, I'm a little bit confused here because there is no salt is given, which means it will act as an amphoteric thing. So let me write it down. H2PO4 negative is basically proton acceptor. So when it is treated with H plus sign, it will turn to an acid. So it's going to be H3PO4. And it can also donate its proton very easily because it has an amphoteric nature. So when we added hydroxide ions or sodium hydroxide in a very small amount, it will turn to water and HPO4 2 negative. I hope it makes sense to you. This ion has an amphoteric nature. Okay. Next part is An alternative answer um, could be written, can be written as, that's an alternative answer, guys. This H2 PO4 negative when treated with hydroxide ions, it will get water and HPO42 negative, right? Um, so this is going to be a salt because it has less proton. So this salt can accept proton and convert it into dihydrogen phosphate ion. So this could be an answer too, but I'm sure this is acceptable in the paper. I believe both of them are acceptable. Both of them needs to be acceptable in the paper. Needs to accept in the paper. The solubility of calcium phosphate is 1.14 into 10 to the power minus 7 mole per dm cube at 25 degrees Celsius. The expression for the solubility product of calcium phosphate is shown. Calculate the value of the Ksp for this compound, including the units. So concentration of calcium phosphate is given. So let me write down the equation first. When calcium phosphate ionizes, it will turn to calcium ion and phosphate ions. We know that both of them has 1:3 ka ratio. When we have 1.14 into 10 to the power minus 7, obviously the concentration of calcium ion is going to be 3.42 into 10 to the power minus 7 mole per dm cube. Okay. Now in the second step, we know that calcium phosphate and phosphate ion has 1:2 ratio. Let me get the concentration of phosphate ion. So it's basically 1.14 into 10 to the power minus 7 into 2. So it's going to be how much? 2.28 into 10 to the power minus 7 molar. Now I'm going to plug in these two values in the formula in the expression given in the paper, and I'll get the value of Ksp. So concentration of calcium ion and concentration of phosphate ion. Concentration of calcium ion has a power of cube because we have 3 moles in the formula. So calcium ion is 3.42 into 10 to the power minus 7 cube. Phosphate ion has 2.28 into 10 to the power minus 7 is square. So the value of Ksp is 2.079 into 10 to the power minus 33. And the unit is basically mole 5 dm minus 15. So value is going to be 2.079 into 10 to the power minus 33. And the unit is going to be mole 5 dm minus 15. I hope it makes sense to you. All right. Now in the next part, some solid sodium phosphate is added to saturated solution of calcium phosphate. Predict the effect, if any, on the solubility of calcium phosphate. Explain your answer. That's called common ion effect. Let me show you something here. Let me have a beaker here. In this beaker, we have a saturated solution of calcium phosphate. Okay. So this calcium phosphate has a saturated solution. Obviously, an equilibrium is established between dissociated and undissociated form like this. All right. So when you add sodium phosphate, obviously the concentration of phosphate ion in the solution increases, and this favors the equilibrium towards left hand side. When equilibrium favors left hand side, that it means um, amount of ions decreases and amount of solid increases, which means precipitation increases and solubility decreases. So solubility of calcium phosphate decreases when we add sodium phosphate in a saturated solution of calcium phosphate. Let me write the explanation here. When sodium phosphate is added, it increases the concentration of phosphate ion in a saturated solution. This favors equilibrium towards left hand side. Hence, precipitation increases and solubility decreases. And when we say solubility decreases, that means amount of ions decreases in the solution. All right. So that's the end of this question. Let's see what we have in the next. Oh, organic. And that's my favorite. Methyl benzene reacts readily with nitronium ion, NO2 plus. Nitronium ions are generated by the reaction between concentrated nitric acid and concentrated sulfuric acid. Write an equation for the formation of nitronium ion. So that's what we have done in the class. 2 moles of sulfuric acid reacting with 1 mole of nitric acid, converting into hydrogen sulfate ions, hydronium ion, and nitronium ion, NO2 plus. Okay. And obviously, it's not stable, which is why ultimately it will turn to water. Okay. So I'm not going to use this as an electrophile in the mechanism. Complete the mechanism in figure 6.1 for the nitration of methyl benzene to form 1-methyl-2-nitrobenzene. Identify all relevant curly arrows and charges. By the way, in order to write the organic intermediate, you must have a sound knowledge of resonance. And because in resonance, there must be a charge oscillation on certain carbon atoms, so you should have an idea on what carbon atoms the positive charge is oscillating. And as per that oscillation, you need to write the organic intermediate here. So this pi bond interacts with nitronium ion. This arrow will give you 1 mark in the paper. Let me write the organic intermediate. Since examiner attached NO2 with this carbon atom, so this CH3 group will remain as it is. I need to show hydrogen, and I need to attach nitronium ion with this carbon. Now this electrophile is attached to this carbon, which means apart from this carbon, I need to show pi complex like this. And you need to take all the carbon atoms from here to here, because positive charge is oscillating on this carbon atom, and this carbon atom, which is why I need to take all these three carbon atoms in order to make the pi complex, or in order to make the horseshoe shape structure. All right. And that's what we have done. You can check the explanation in my lecture. Okay. Now I need to remove this positive charge from the benzene ring, because benzene is certainly electron deficient, which is not a quite suitable situation. So to get the stability, I need to remove that positive charge, and for that, benzene needs electron. How can we get the electron? By shifting this bond into the ring, and hydrogen is removed in the form of hydrogen ion. So I'll get the product and this hydrogen ion. Okay. I hope it makes sense to you. This very, very important. You know, you cannot write this thing. If you write this thing, if you write pi complex like this, you will not get a mark. Either you need to write this, or either you need to be very, very accurate like this, from that carbon to this carbon. Okay. Cannot get a mark. And don't write in this way. Do not ever write like this. If you write pi complex like this, examiner will cut the mark. Okay. You will not get the mark for that. Phenol can be nitrated with dilute nitric acid. Explain why nitration of phenol occurs under milder conditions than the nitration of benzene. Because phenol contain OH group, and OH is an orthopara directing group. So it increases the electronic density on orthopara position, and orthopara position are 2, 4, and 6 position. All right. So OH is an orthopara directing group. It donates electrons into the benzene ring. So it increases the reactivity and electronic density. Electronic density. And reactivity of the benzene ring. Technically, OH group increases the electronic density specifically on ortho and para position, and those ortho para positions are 2, 4, and 6. That means the negative charge is oscillating on 2, 4, and 6 position. Okay. Which is why nitration of phenol requires milder condition than benzene. Okay, next part. A sample of 2-nitrophenol is reacted with sodium. Complete the equation in figure 6.2 for the reaction of 2-nitrophenol with sodium. So sodium is reactive metal. It places hydrogen in the form of hydrogen gas. So I'm going to get hydrogen gas, obviously, and a salt. This oxygen atom will remain. Instead of hydrogen, I'm going to write sodium, and this NO2 will remain. So we have 2 hydrogen here. So in order to balance the equation, we need to put 2 here, 2 here, and 2 here. Now it's a balanced chemical equation, okay? This reaction is also called displacement reaction. This reaction is also called uh, redox reaction. Why redox reaction? Because sodium is oxidized from 0 to +1 oxidation state, which means it is oxidizing. Oxidation takes place in sodium, whereas reduction takes place in hydrogen because it changes its oxidation state from +1 to 0. Okay, I hope it makes sense to you. Next part of the question. 2-nitrophenol can undergo different reactions as shown in figure 6.3. Suggest reagents and conditions for reaction 1. So that's very easy. See, the entire molecule will remain as it is, but only NO2 changes into NH2. So whenever NO2 changes NH2, we need reducing agent, and specifically we need tin concentrated HCl, and the condition is reflux. Okay. Now both NO2 and ethanol chloride cannot react together. They are inert to each other. They are chemically unreactive towards each other, all right? But OH can react with ethanol chloride. And when OH can react with ethanol chloride, reaction is going to be nucleophilic substitution reaction. But the examiner is looking for the name, the type of reaction for reaction 1. That's reduction beta. Because I'm using reducing agent. Reaction 2 is carried out at room temperature. That's very, very important information. Draw the structure of the organic product. Okay. So what's happening here is H and Cl combine together to give HCl. Now the remaining part of the reactants react together to give a product. So I'm going to write the product here like this. This is oxygen. This is C double bond O. And then CH3. Okay. So that's the organic product. That's ester actually. Name the mechanism for this reaction. Obviously, it has a lot of reaction because removal of HCl is condensation, right? So I'm removing HCl. That means I can write condensation because loss of mass takes place in terms of HCl. This phenol is acting as a nucleophile also because oxygen has a lone pair, which means I can say it's nucleophilic. Addition reaction. Why nucleophilic addition reaction? Because both these two compounds are reacted together and form a product. Since HCl is removed during the reaction, also called elimination reaction. So this reaction has multiple sort of names, but I think these two are the most common ones. The NO2 group in 2-nitrophenol is electron withdrawing. Electron withdrawing means this group will withdraw the electron from the benzene ring. So if electron withdraw the electrons from the benzene ring, obviously the electronic density on the carbon atom decreases, and so reactivity decreases. So whenever any electron withdrawing group is attached to the benzene ring, that group decreases the reactivity and electronic density of the benzene ring. And that's what we have done in the class also. Suggest the relative acidities of ethanol, 2-nitrophenol, phenol, and water. Explain your answer. Most acidic is 2-nitrophenol. Then phenol, because phenol is a weak acid. Then water, because it does not have positive inductive effect. And then ethanol. And ethanol is the weakest one because it exhibits positive inductive effect. And that positive inductive effect uh, uh, decreases the ionization of hydrogen in water. All right. So 1 mark is there and remaining 3 marks for the explanation. Okay. NO2 withdraw the electrons from the benzene ring. All right. As a result, ionization of hydrogen becomes easier. Due to strong electron pulling effect. Okay. Now phenol has a resonance process. So it anions is more stable. So its anion is more stable than water. Ethanol has an alkyl group. Due to which it has positive inductive effect. As a result, ionization of hydrogen is not possible or is not easier. So that ionization of hydrogen is not easier. As electronic density on oxygen atom increases. So electron pulling effect becomes weaker. Okay. Let's move on to the next part of the question. Part F. Silbupetrol is a pharmaceutical drug that contains a phenol functional group. Name and classify the three other functional groups in this product or in this compound. So first of all, this is primary alcohol. This is secondary alcohol. This is secondary amine. Okay. Name of functional group, hydroxy. And obviously this is going to be phenol. This one. The second one is alcohol, and both contain primary and secondary. And then we have amine. It must be aliphatic secondary amine. Silbupetrol reacts with aqueous bromine to form organic product X. Draw the structure of X. C. OH is an orthopara directing group, and obviously it increases the electronic density on orthopara position. Let me tell you the position of orthopara. This one is the first carbon. This one is second. This one is third. This one is fourth. This one is fifth. And this one is sixth. Now, second carbon, fourth carbon, and sixth carbon is basically orthopara position. So bromine needs to attach on these three positions, right? Issue is that 2 and 4 position are already occupied with certain groups, which means aqueous bromine is only attached to the 6th carbon atom or that particular position. This is OH. Okay. This is NH. Okay, hold on. I need to add one hydrogen. Oh, that's the right one, yeah. And then we have this one. So I need to attach bromine here only because second and fourth carbon atom are already occupied with these groups. Okay, so that's the structure of X. Silbupetrol reacts with excess of thionyl chloride to form organic product Y. The molecular formula of Y is this. Draw the structure of Y. Okay. So thionyl chloride reacts with alcoholic functional group, and obviously it will react with these two groups, right? So we have two chlorine atoms. Oh my goodness. Oh, let me write it down again, the whole structure. Thionyl chloride reacts with alcohol, not with phenol. The phenol functional group will remain as it is. Now this primary alcohol react with thionyl chloride. So instead of OH, I'm going to write chlorine here. I'm going to write chlorine here again. This NH will remain as it is. And this entire group will remain as it is, okay? So that's the structure of this organic product Y. So that's the end of this question. Let's move on to the next one. Question number 7. All right. Now the next question number 7 is 2-amino butane exist as a mixture of two enantiomers. Enantiomers basically mirror images of each other. Define enantiomers. They are mirror images of each other. And they will rotate plane polarized light. Equally in opposite direction. Explain why an aqueous solution of 2-aminobutane has a pH greater than 7. Include an equation in your answer. Since examiner is talking about an aqueous solution, which means 2-aminobutane is placed in water. So this is 2-aminobutane. It will turn to CH. Now NH2 is proton acceptor. When it accepts proton, it will turn to NH3 positive, OH minus, and rest of the molecule will remain as it is. Okay. So what we need to write here is it is soluble in water. Because NH2 will accept proton. All right. And therefore, pH of solution must be greater than 7.0. Next is 0.1 mole per dm cube solution of diethylamine has a higher pH than 0.1 mole per dm cube solution of 2-aminobutane. Now look, both the solution have same concentration, but one has higher pH and the other one has lower pH. This one has a higher pH because this compound contained two electron donating alkyl groups. So this compound has stronger positive inductive effect as compared to this compound. Okay. Because of a strong, because of a stronger positive inductive effect, of two electron donating alkyl groups, electronic density on the nitrogen atom increases. So lone pair is easily available for protonation. Look, what's happening here is this is NH. Now you have one ethyl group here, and another ethyl group here. Now these two alkyl groups are directly attached to the nitrogen atom, which means these two groups has a stronger positive inductive effect because they donate lone pair onto the nitrogen atom, which is why the lone pair on the nitrogen atom is easily available because of the higher electronic density. So if two electron donating alkyl groups are attached to nitrogen atom, these two groups have a stronger positive inductive effect, which means these two groups donate electron towards nitrogen atom, and therefore this nitrogen has more electronic density, and therefore this nitrogen atom has the lone pair of this nitrogen atom is easily available for protonation. On the other hand, what's happening in this compound? Let me show you. This is CH3. This is CH. This is NH2. This is CH2. This is CH3. Now, this compound also has two electron donating alkyl groups, but both of them donate electron to the carbon atom. All right. So these two electron donating alkyl groups are indirectly attached to NH2, which is why, as compared to this scenario, the electronic density on nitrogen atom is relatively weaker and lower. So lone pair of nitrogen is not easily available for protonation in this scenario. Okay, I hope it makes sense to you. Next is diethylamine reacts with ethanoic acid. Complete the equation for this reaction. So obviously it will accept proton and will turn to NH2. Oh, diethyl. CH3, CH2 taken to NH2 positive. Okay, so this is acid. It donates its proton. It is an alkali, so it accepts proton, and as a result, you will get CH3, CW negative. Okay. Now, in the next part, this compound reacts with ethanol chloride. Complete the equation for this reaction. Now, this hydrogen and this chlorine combine together to give HCl. Now we need to join the remaining fragment of the molecule. And the remaining fragment is like this: CH3, CH2, taken to N. N is attached to CO and C is attached to CH3. And that's basically an amide. Okay. I hope it makes sense to you. Okay, how amides are formed. Okay. In this scenario, we can make an amide, but for that I need heat. Since there is no instruction is given in the question, which is why I've done acid-base reaction here. Next part of the question related to polymerization. Complete table 7.1. Okay, this is carboxylic acid. This is acyl chloride and alcohol. I mean to say two different functional groups are present on either side of the carbon atom. And this compound has double bond also, guys. Look at this carbon. This compound has double bond here. And this compound has COH and NH2. So type of polymerization, whenever we have double bond between the carbon atom, polymerization is going to be addition. Whenever we have this sort of compound, it's going to be condensation. You know, this is amino acid. Amino acid always undergoes a condensation reaction to give a protein chain, because amino acids are the building block of proteins, right? Ethane dioic acid can react with propane 1,3-diamine, all right, to form a polymer W. Draw a section of polymer W showing one repeating unit only. The new functional group form should be displayed, okay? Oh God. So obviously from here OH is removed and from here H is removed. And as a result, water is produced, right? So if COH gives OH during the reaction, this COH also gives OH during the reaction. On the basis of that, let me show you the bond continuation. OH has gone, C double bond O left, then C double bond O, and then NH, then this CH2, and this CH2 1, 2, 3 times. So I can write CH2 taken 3, then NH. Now the next is CO, then again CO, then again NH, and this is going to be CH2 taken 3, NH, and this bond continuation. Now look at the structure from here to here, from here to here is the same repeating unit, right? So that's the structure which is going to be acceptable in the examination paper. I hope it makes sense to you. Let me give you an equation here. Give you an equation. This is COH. This is COH plus NH2, CH2 taken 3, NH2 plus COOH, then COOH plus NH2, CH2 taken 3, and then NH2. All right. Now OH is removed from carboxylic acid and H from amine. Same here, OH is removed from carboxylic acid, H from amine. Same here, OH is removed from carboxylic acid and H amine. And same here, OH is removed and hydrogen is removed from here. So the equation is going to be like this. And that's your product, okay? polyalkenes biodegrade very slowly. Explain why. Because of the lack of functional group. Because they are chemically inert and they have a strong carbon-carbon bond. They are non-polar as they are hydrocarbons. All hydrocarbons are non-polar. That's what we have done in AS. So polyalkenes are non-polar hydrocarbons, do not have any functional group. Also, they have a strong carbon-carbon bond. All right, that's the end of this question. Let's move on to the next one. Let's see what we have in the next question. That is question number 8. Oh my goodness, that's proton and C13 NMR. That's my favorite. Compound A is analyzed by carbon 13 NMR and proton NMR spectroscopy. State the reference substance and a solvent that can be used in NMR spectroscopy. Well, we have told you tetramethylsilane is used as an internal reference solution. In short, we can say TMS. This internal reference solution is used to calibrate the apparatus, okay? Solvent needs to be either CdCl3 or D2O. All right, so either we can use CdCl3 or D2O because deuterium cannot absorb radio frequency radiations, which is why deuterium cannot interfere with the hydrogen of the sample. All right, predict the number of peaks in the carbon 13 NMR spectrum of A. Okay, let me show you the number. This one is first, this one is second, this one is third, this one is fourth. Okay, this one is 5 and this one is 6. These two carbon atoms are joined with carbonyl group. I can see that also. But these two carbon atoms doesn't have same chemical environment because this carbon is also attached with oxygen and this carbon is attached with ethyl group, which is why these two carbon atoms have different chemical environment. All right. I hope it makes sense to you. And these two carbons are attached with the same distance with this oxygen atom, which means both the carbons have same chemical environment. Both the carbons experiences same electronegative uh, element factor because of the same distance. Okay, so there are total 6 carbon atoms in C13 NMR. The proton NMR spectrum of A shows peaks in 4 different chemical environments. Okay. Let me write down the structure first. CH3, CH2, COO. Let me write down the structure so that I can apply the n+1 rule and so that I can fill these above columns CH3, CH2, CO, this oxygen, this is CH, this is CH3, and this is CH3. All right. Now let me apply n+1 rule here. Now neighbor has 2 hydrogen atoms. So 2 plus 1 is going to be 3. That's your triplet. And this triplet has a chemical shift of 0.9 to 1.7 delta. Okay. Now this CH2 has 3 neighbor hydrogen atom. So it's basically 3 plus 1, 4. 4 means quadrate. and quadrate with carbonyl group indicates 2.2 to 3.0 delta. Okay. Now this carbon atom has 6 hydrogen in its neighbor. So if I'm going to apply n+1 rule, there's going to be 7. When we have 7 peaks, according to my lecture, it's going to be septate. And since this carbon is attached with more electronegative oxygen, so its chemical shift is going to be 3.2 to 4.0 delta, okay, according to the data booklet. Now, guys, you know that these 6 hydrogens have same chemical environment. Which means if I'll use n+1 rule on that carbon, so it has only 1 hydrogen in its neighbor. So obviously it's going to be 2, is going to be doublet. And obviously this is alkyl, so 0.9 to 1.7 delta. Okay. So 3.75 is basically splitting pattern. Splitting pattern. This carbon has 6 hydrogen atom. So splitting pattern arises because of 6 hydrogen atom. Number of protons on the adjacent carbon atom, 1. Okay. This one has 1 carbon atom and its 6 neighbor. The number of protons responsible for the peak, oh no, hold on. Splitting pattern is basically septate. You can write multiplet also. Number of protons on adjacent carbon atom, 6. And number of hydrogen atoms responsible for the peak, 1. Now 2.85 is basically here, right? So 2.85 gives you quadrate. And this quadrate arises because 3 hydrogen atoms exist in its neighbor, and proton responsible for this is 2. I will not write 2H here. I will not write 1H here because examiner didn't show any hydrogen with this number. All right. So I need to put 2 and 1 as it is. 1.5, 1.5, 1.5. 1.5. I think 1.1, 1.5 is doublet. Because these 6 hydrogen atoms indirectly attached to oxygen. So oxygen has more electronegative impact as compared to this carbon on these hydrogen atoms. Okay. So doublet arises because of 1 proton. Okay. And neighbor has 6 hydrogen atom. Last but not the least, splitting pattern is triplet. Arises because of 2H. And neighbor has 3 hydrogen atom. Okay. I hope it makes sense to you. That's easy, by the way, because if a structure is given, you need to apply n+1 rule, and then you will get the splitting pattern. And if you get the splitting pattern, you will get the chemical shift value from the data booklet, and that's what we have done in the class. And you can accommodate this question very easily. Question is going to be very, very difficult if examiner gives you certain amount of information from this chart, and examiner wanted to see the structure of organic molecule, and that's going to be very, very tough, not an easy task. So let's move on to the next question. That is question number 9. This question seems related to amino acid. The structure of amino acid, serine and lysine as shown. Okay. The side chain of serine is polar because it has CH2OH group, polar functional group. The side chain of lysine is basically um, neutral because, and also it has an alkaline nature because NH2 is proton acceptor. Draw the structure for the dipeptide serine lysine with molecular formula. The peptide functional group form should be displayed. Okay. Now there are multiple options here. What we can write here is this NH2 and this COH react together, and that is the most easiest way of writing the structure. Most easiest way. Otherwise, this NH2 and this COH can react together. The third possibility is this CH2 and this NH2 can react together to give a structure. So there are multiple uh, sort of structures can be possible for dipeptide. All right. So I'm gonna go for the easiest one, that OH is going from COH and H is going from H. The rest of the molecule will remain as it is. See, this is NH2, CH, this is CH2OH, this is C double bond O. Now this has NH, this is CH. Now this carbon has side chain 2, 3, 4, and NH2, and this is COH. So that's the most easiest way of writing the structure. Okay, most easiest way. Now the B part 1 is state what is mean by isoelectric point. By the way, the isoelectric point for serine is 5.7 and lysine is 9.7. So you must remember this. Isoelectric point of serine. Isoelectric point means when there is no net electrical charge exist. When no net electrical charge exists, or zwitterionic form or exist in zwitterionic form is isoelectric point. This is basically electrophoresis we have done in class. Okay. The mixture of serine, lysine, and this dipeptide is analyzed electrophoresis using a buffer at pH 5.7. Buffer at pH, buffer solution की pH is given, which is 5.7. And the isoelectric point of serine and lysine is also given. So with respect to these pH values and this, I can easily suggest adsorption and deprotonation and protonation takes place. Okay. C. Isoelectric point of serine and pH of buffer is same, which means serine will not show any sort of deflection and will remain present on this spot. Okay. So serine has to be here. Okay. Now lysine has a pH of 9.7 and the pH of buffer is 5.7, which means NH2 will accept proton. If the pH of buffer solution is lower than the isoelectric point pH, then protonation takes place. That's what we have done in the class. So if lysine accepts proton, is going to be positively charged, and this NH2 will accept proton also, and so it will turn to positively charged. Now this is positively charged, and since it has 2 plus charge, so it will show more deflection and will cover the most distance. So lysine will cover the most distance. So this is going to be a lysine. Since it has more charge, so it shows more deflection. Now the dipeptides serine and lysine will cover the least distance. It has to be here somewhere. And obviously serine and lysine, this dipeptide has higher MR. If its MR is higher, obviously it has less charge. And obviously it shows less deflection. Okay. So all the amino acids and dipeptides exist as cation, and so they will deflect towards negative terminal. Okay. So explain your answer. And that's my explanation actually. Serine, no deflection. As pH is same. So exist as neutral. Okay. So let me write down. So serine has same isoelectric pH with pH of buffer. So it shows no deflection. Lysine has higher isoelectric point pH. So it undergoes protonation. So exists as cation. And shows more deflection towards negative terminal. Dipeptide is this. Obviously, its pH is greater than the pH of buffer solution, which is why it will accept proton. It undergoes protonation, and so it will deflect towards negative terminal. But it has lysine and serine has higher MR lower charge, less deflection. Okay. Oh my goodness. Next is figure 9.3 shows the synthesis of compound R from compound P. That's an amide. And this amide undergoes hydrolysis. Okay. Okay. What we can do is, let me show you what's going on actually. Okay, let me show you. Okay. So during hydrolysis, C single bond nitrogen, carbon nitrogen bonds broken. This CO will get OH of water. And there's a shortcut technique, you know. We have done this in class. And this nitrogen will get hydrogen of water. As a result, I'll get this compound. This is C double bond O. We are getting OH of water. And this is NH2. Okay. So in step 1, hydrolysis takes place. So draw the structure of Q. So this is the structure of Q, which I'm going to write. Okay, this is the structure of Q. And in step 1, acid hydrolysis takes place because examiner is looking for the reagent conditions. So acid in the presence of water and condition is heat. Okay. Now in step 2, this compound convert into this. I mean, this carboxylic acid is converting into an ester, which means I need to swap these two functional groups. Let me show you how can we swap this functional group. Let me write this structure again. This is C double bond OH. This bond is here. I'm going to put OH over there. This OH shifts there. And this entire group shifts here. This is NHCH2 and then NH2. Okay, I hope it makes sense to you. This CH2 and NH2 is here. This carbon has OH, this carbon has OH, it will shift here. Now what's going on actually? Actually dehydration takes place, removal of water takes place. When you remove water, you will get what? This is oxygen and this is oxygen. And that's what the examiner has done here. I hope it makes sense to you. So in step 2, dehydration takes place because I'm removing water. And for dehydration, we need concentrated H2SO4. and the condition is again heat. So that's the end of this question. I hope it makes sense to you. Thank you very much, guys. That's the end of the paper.